Welcome to Artificial Intelligence Foundation and Applications course. Today we will talk about constraint satisfaction problem. So there are a set of problems which have a similar nature, and those problems can be addressed in a similar structure. So earlier we have seen that search technique can be used to solve the problem optimally, or any kind of satisfaction problem can be solved using search technique, but that's a kind of a generic one. And for certain problems, when we find that there exists a certain structure, we can actually exploit that kind of structure in stuff from the problem, and we can model it in a unified manner. So let us first look into a few problems, and then we will see how to model those problems in constraint satisfaction environment. So to start with CSP problems, so let us look into few examples. One of the most common example is uh, one of the most common example is the crossword puzzle. So you will be given a crossword, and there will be a set of uh, so let's say this is the crossword, and there will be few block which will be filled with kind of a black, and you have to put some kind of a character so that it makes some sense or certain kind of a condition. So it has to ensure that uh, the row as well as the column that makes sense when I put some character in this place. So this is a crossword puzzle. We will see few examples in queens on chessboard, which is also a common problem, like when we need to place a set of queens on this chessboard such that no queens is attacking each other. And you may be familiar with that in a chessboard, queen can move horizontally, it can move vertically, as well as it can move diagonally. So you have to ensure the set of queens, you have to place the queens in such a way that none of the queens is attacking each other. Then there is a knapsack problem. I'm not going to elaborate all those problems. Few I will elaborate in next of the slides. Assembly scheduling, like in a workshop, you have to schedule the set of jobs in such a way so that you can minimize the make span, or you try to optimize certain other things. There are a lot of problems in operation research which can fall into CSP category, and there are many other problems, like if you want to color a map, there will be a set of constant, like if I have a map, and if some of the countries are sharing a boundary, then I cannot put red here as well as red here and this green. Only thing I have to ensure that two countries that share a common edge, they should not have the same color. Timetabling is another problem, like for a academic institute, it has to prepare a timetable, a student, a course, a room, and a slot. You have to specify, because at a point of time a student should not be attending two courses, because which is not possible. At the same point of time, two courses cannot be scheduled on the same room. And there are many other constraints, like if a faculty has more than one subject to teach, then you cannot arrange those two subjects in the same time slot. So there are few constraints that you have to ensure, so which is a pretty common problem. And same thing we can see in the airline and the train scheduling. There are many other problems, like cryptic puzzle we will see with an example, boolean satisfiability, card sequencing, scenes labeling, and there are many other problems. They have a similar structure, and that can be modeled using CSP. So we will look into that part. So let us first look into the situation, how we can model a CSP problem. To model a problem in CSP, we need to have a set of variables, and we call this set of variables as the decision variables. That means we define a set of variables x1 to xn, and which we have to determine eventually. So this xi's will take certain values from certain domain, and the whole problem will be described around this decision variable. So first is the variables, decision variables. Then for every decision variables, what we need to do is we need to specify the domain of those variables. Like, it can be a situation that x1 can take value only 0 or 1, this xn can take value from 0 to 10, so on and so forth, and maybe this can take any value between 0 to 1. It can be a real number as well. So for every variable we have to define the domain in which it can take the value. Then the set of constraint, like when we try to model the problem, we need to ensure a set of constraint. The one of the example that I was talking earlier, like if I have two countries that shares a boundary, then I cannot give the same color. I cannot put R red and red here, but I can put green here. So we have to define the set of constraints, and this constraint will be based on this decision variable, and there can be few other parameters which can be an input as well. So one thing is that we have to define this set of constraint, and this constraint can be unary, this constraint can be binary, and these constraints can have many variables. That means I can only specify, like when it is a unary constraint, I can say like x1 is less than 5. So that is an unary constraint. I can have binary constraint like x1 is less than x2, and it can be it can have more than one variables, like I can say x1 plus x2 plus x3 is less than say 5. So that can be the constraint. So given the value of the variables, and if you have any constraints, if you replace this variables with the given values, then this will yield either true or false. So the constraint is basically it will yield either true or false, or yes or no, once you know the values for each of those variables. So that is we will see how to write the constraint and how we can actually model those constraints. Then there is an optional one. Sometimes it may happen that we can have a few objective function which we would like to optimize, which can be we would like to minimize or maximize certain things. So for certain problems we can have those information as well. And finally when we find the solution, so this this is will be required to model the problem, and once we solve that stuff we get a solution, and solution is nothing but a consistent assignment of the domain values to each of the variables. So I have these values for each variable. I have the domain. So once when I'm saying a solution, that means I will say x1 takes the value say d1, and this d1 should lie in d1, capital D1. Similarly for the other variables, and all the constraint that is specified here, so c1 should be, all this should be actually true. When we replace this constraint with the actual value d1 d2 and so c1, let's say c1 depends on x1 x2 x3, and if I replace this x1 with d1, x2 with d2, x3 with d3, then this will yield actually yes for me. And if it does not yield yes, that means the constraint is not satisfied. And so if you are solving only the satisfaction problem, if it is satisfied then it's fine, and for if I have some optimization criteria, then we would like to optimize that criteria that is actually met. Now let us look into problem how we can actually model this one. So let's say I have this n queens problem which we talked earlier also. So given this checker board or the chess board, and I have to place n queens such that no queens are attacking each other, that is the constraint. So so there are many ways we can model this problem in constraint satisfaction, and we will see a few of those stuff here. So let us define the set of variables. So we define the variables in this way: xij. So what does this xij means? We mean that in cell ij a queen exists, or queen is in cell ij. So let's say this is my ijth cell, and if this is 1, then the queen is present in this place, and if it is 0, then the queen is not present. So we define the variables and we define the domains for each of those variables. So you can easily understand that ij, if it is 8 cross 8 or if it is n cross n, then I will be less than n, less or equal to n. Similarly your j will be less or equal to n. So effectively we are defining n square number of variables. Fine. And then we have to define the set of constraint. So what is the constraint it has to satisfy? So first of all, that in each row I can have only one queen available. So what we can do, we can say that if I sum this value, or if I sum xij, then it will yield actually 1 when I when I vary this I. So this will be kind of this will be in term either row or column, depending on how are you using this index variable I and j. Similarly, if you look into this stuff, this column, then I will also have this to be 1 as well. So only thing you have to be careful which index is referring what. So if you refer I along this, so if I along this, then the first constant that you have seen, that means it basically represent the column sum, and if j is on this side, then this will be the sum along the row. Fine. So so only thing is that we have to have uh, row sum will be 1, column sum will be 1, and if I sum over all the elements, then it should not exceed n, because we are allowed to put only in queens. Now also what we have to do is that if I place a queen here, then I cannot place a queen in any one of these diagonal side, so which we can actually represent through this condition. So if I place queen here, then I cannot place any queen on the kth side, so I cannot put any queen in the any diagonal direction, and k value has to be chosen in the appropriate range. So here what we are saying that if this is ij, then I am just adding I plus k, j plus k, so it will be one diagonal element, or it will be I plus k, I am increasing the row, and but it is in the opposite side. So if we put this set of constraint, then and then we can give this set of constraint to a solver, and the solver will give us the solution. So for today's lecture, we are not going to see how to solve this one, but to how to model the different problems using this constraint satisfaction way. Now if you look into this problem, we have already said that we have n square number of variables, and if you are solving for 8x8 checkerboard, then the search space will be a pretty huge number, because we have 64 cell and each cell can take 2 values, so therefore the total number of possible ways is 2 to the power 64, and out of those 2 to the power 64 there will be a few set of solutions that we would like to find out. Now we will look into an alternative model for the same problem. So it was the same stuff, same problem. Now we are defining the variables only as xi, so effectively x1 to up to x8, and each variable, what we say, that each variable can take values 1 to 8. Fine. And now we have to define the set of constraints. Now if we, so what will be the situation? So effectively this x1 means the position, it is the position of queen, is the position of queen in row 1, right? Now we have to write the constraint based on that way. So what will be the constraint? Like say I can the constraint will be like if x1 is 1, let me write it in this way, x1 is 1, this implies, or or the constant I can say, if x1 is 1, then uh, or then I can say like x2 equal to 1, it cannot happen. Or I can say, so this will be true for all the values. So effectively I can say x1 is not equal to x2, because whatever value you choose, x1 and x2 cannot have the same values, because that was the thing. Fine. Similarly, so so that is one of the thing. So what you have to do, using this set of variables, you have to specify that 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 there is uh, no more than one queen in each row, and that is being ensured by these variables, because we have only one variable for each row. Only thing now what we have to do, we have to specify that we do not put a queen here as well as another queen here, because if I have this situation, then it is a invalid configuration. Also what we have to do is, like, if I put one queen here, then I cannot put a queen in this place, and I cannot put a queen in this place similarly, and so on. So I have to write the constraint again in the similar manner. uh, uh, Again we have to write a constraint in the similar manner, that we cannot put queens along the diagonal element. So I leave that constraint for you as an exercise. You can write those stuff, those constraint. Now let us look into the other interesting thing. Like earlier we have seen that we have a very large space, 2 to the power 64. Now if we model in this way, we reduce the search space to a very significant extent, because we have 8 variables, and each variable can take 8 different values. So the number of uh, possible states that can have is 8 to the power 8. So it is a very significant reduction in the number of variables, so which sometimes actually help depending on the problem. So our target will be to reduce the search space. The more we reduce the search space, it is expected that the problem can be solved easily to some extent. So we have looked into the same problem into different ways to model. There can be other variant of this problem that that you can take as an exercise, that you can have an additional constraint, like at least a queen is on the main diagonal. So I have to ensure that one queen must lie on the actual diagonal. Then a little bit more one, 2 queens on the 2 main diagonals. So there is an additional constraint. And then the another interesting problem is like how to enumerate all possible solution. So all these problems can be modeled in CSP. So the first two problems is fine, only thing you have to add few extra constraints, but we will see how we can do, or how we can enumerate all solution at a later stage. So let us look into another problem. So this is to prepare an examination schedule. So given a set of subject S1, S2, S3, this is the set of student S1 to S5, and each student has opted for these courses C1 to C6, or that table has been given to us, and we have to prepare a examination table, examination timetable, and the condition is something like that, is it possible to conduct all these exam in 3 days, assuming one exam per day. So when we ask this question, then we have to ensure that a student will be able to write only one paper per day. So I should not schedule C1 and C2 on the same day, because in that case S1 will not be able to answer the papers, because he will be able to appear only in one exam. So in order to model this problem, we uh, we what we do is we try to model this as a graph problem, or maybe we can construct a graph that can give us some idea. So what is the graph that can be constructed? The graph that we construct here is based on the subjects, because we have to schedule the subjects in every day. Now we have this subject C1, C2, C3, C4 up to C6. Now if two exam cannot be conducted on the same day, then we connect these two subjects with an edge. For example, like C1, C2 we cannot conduct on the same day, so we have connected with an edge, because in that case S1 will not be able to write an exam. C1 to C6 is connected because S5 will not be able to write the two exam on the same day. So I have to ensure that C1 and C6 are scheduled on a different day. So given this information, we can construct a conflict graph which will describe me that what are the subjects we can conduct on the same day. Now if you look into this graph, this conflict graph, then I can very easily say that C1 and C4 can be conducted on the same day. Similarly, I can say C2 and C6 can be conducted on the same day. So this graph gives me some idea which exam can be conducted on the same day, which exam cannot be conducted on the same day. So which you can conduct on the same day, and which you are not be able to conduct on the same day. Now this is one of the very famous interesting problem in the computer science theory. So in order to schedule that stuff, what we need to do is we need to assign some day. So for example, what we can say, we say that we conduct this exam on D1. So we can say this exam can be conducted on day 1. Since I cannot conduct C2 on the same day as D1, so I say let me conduct in D2. C3 I cannot conduct on the same day as D1 and D2, so I conduct it in D3. Now if you look into C5, which I cannot conduct on D1, I can conduct on D2, but I cannot conduct in D3. Now if you look into C6, then I can conduct it on D2. Sorry, I cannot conduct it on D2 because then C5 is in class, but I can conduct it in D3. So this is just one of the solution that can be figured it out. So instead of saying as D1, D2, in computer science theory, what we say, this is some kind of a color. We try to assign some color maybe I can call this as red, I can say this as green, this as blue, and so on so forth. So that means when I'm assigning some color, I need to ensure that the two nodes across an edge should not have the same color, or the two nodes that shares an edge should have the different colors. So these days are nothing but some kind of a color that we are actually assigning. So it is one of the famous computer science problem is known as graph coloring problem. now now the thing is how to model this problem as a CSP. So the thing is, what we need to do is we need to define the set of variables, so which is x1. So for every subject I need to assign a day. So we say that subject ci is being allocated in slot xi. So for xi, and for every xi the domain can be 1 2 3 because I have only 3 days to schedule. And what are the constraint that we can write? The constraint will be something like this, like x1 cannot be scheduled with x2, x1 cannot be scheduled with x3, similarly so and so on. So we can write the set of constraint in this way, and you can elaborate all those constraints. So I have not written all those constraints explicitly, but you can write it those constraints. So, and which I have told that it is one of the famous graph coloring problem. Let us look into another problem, so which is airport gate scheduling. So we have a set of flights and they have some arrival time and they have a departure time. Now the thing is, for every flights we know the arrival time and the departure time, and what we need to do is we need to use a set of gates through which we have to schedule all this thing. Now so the question is it possible to schedule all the flights using 3 gates? That is the question. Now what we can do here, again we can go ahead with the similar kind of stuff in the earlier problem, and we can construct a conflict graph, something like this one. So if we have 6 flights, so we have arranged this one. So I have written it c1, c2, c3 and so on. Now if two flights have a overlapping timing, then they cannot be scheduled on the same gate. Like if you look into f1 and f2, they have the overlapping timing, so I will not be able to schedule c1 and c2 in the same gate, so I have connected with an edge. Similarly, if you look into f2, f3, then they are connected with an edge because these two flight cannot be scheduled on the same gate because they have the overlapping scenario. So in order to model this problem, we can actually proceed in the same manner. So we can have same slots. For every slot we have only 3 domain variables because it can be either 1, 2 or 3, which gate we want to schedule. And the constraint is something like this: x1, x2, x1 is not equal to x2, and so on and so forth. And we can, once we write this constraint, we can give it to the solver will give us the solution. And one thing just I would like to highlight here is this problem, it appears to be graph coloring problem as we have seen for the examination scheduling, and this graph coloring problem is NP complete problem, well-known NP complete problem. So there is no known polynomial time algorithm that can find out a solution quickly. For this kind of graph, it has a special property, and we can construct a special kind of a graph, and then we can solve this problem in polynomial time, and this is known as the interval graphs that we can actually construct. So I will very briefly I will tell that how we can construct an interval graph. So what we will do, like if you look into this stuff, then there are flights starting from 7:15 to 10:15. So the whole time horizon is my 7:15 to 10:15. Now flight 1 is from 7:15 to 8:15. That is my flight 1, let's say. So I'm not drawing with respect to scale. Flight 2 is flight 2 is arriving at 8 and leaves at 9, so it will be something like this. Similarly, for the other one, you can actually construct, so it will be some combinations of this stuff. Now once you construct this kind of graph, then you can figure it out easily that how many minimum number of gates will be required, because if you look into at a particular point of time, then how many are actually overlapping with each other. So that is one of the minimum number of gates that will be definitely required, and there is a nice greedy algorithm which will find out the optimal solution, so which is based on the idea of the interval graph. Now let us look into another problem, Cryptarithmetic. So from this problem you can easily understand that you have been given some mathematics in cryptic form. So here you have sent, so when you add d plus e, it yields y. When you add n and r, it yields e, taking into the account of the carry. So now, in order to model this problem in CSP, what we need to do, we need to define the set of variables. So that is the first step. So let us define our variables. So we define the variables by in this way. So S, E, N, D and all the characters, and each character can take a value between 0 and 9. Okay, and the constraint that we can actually write is something in this way. So if you look into this part, then we introduce, let's say we introduce a set of additional variable, like this is the carry for in place C10, this is the carry in the 100th position, this is the carry in the 1000th position. So we have some intermediate internal variables. Now if I have this carry variables, I can actually write the constraint, like I can say d plus e is equal to 10 times C10 plus y. Similarly, we can say uh, C10 plus N plus R is equal to E plus 10 times your C100. And we can also say in this way, like if you look into this part, then if you add S plus M and C1000, then that will yield 10 times M plus O. So I can write all those constraint, and each constant can take value between 0 and 9. Similarly, C10 and to C1000 all are internal variables, so which we usually not bothered, but that will be required to model this problem, and this variable also lie between 0 to 9. Fine, and we can give it to the solver, and the solver will solve it for us. Now here I would like to mention that uh, there exist many public domain tools, open source solver, which can actually solve this problem very quickly, and we do not and these solvers are pretty generic one, so lot of features are available from this solver. So in order to model this problem in one of the open domain solver, we can use this kind of stuff. So this is tool I have used called mini zinc, and if you look into the code that I have to write, is pretty simple, almost like the problem that I have to do. So I define the set of variables. Certain variables can be between 1 and 9, and so that I have reduced, and rest are same. The constant that I am writing is exactly the same as the given expression. And what we need to mention, that all are different, and this constraint, whatever you have, this you need to include, and you have to specify that all ACND are different, and then you just call the solve satisfy. So it is pretty simple to implement in public domain tool as well. Now we will look into a different problem. Till now what we have done, we have looked into the problem which kind of a satisfiability problem. Now we will look into a problem when we need to write some of the optimization function as well. So let us look into the problem, and this is one of the famous problem in computer science domain. So what is the problem? So there are n items, namely O1, O2 to On, and item Oi weighs Wi and provides a profit of Pi. Target is to select a subset of the items such that the total weight of the items does not exceed W and the profit is maximized. So if you look into this diagram, so for every element it has a weight and it has a reward. It has a weight, it has a reward for every object, and you would like to put all the items on your bag, but only the constraint is that you can only support 15 kilo. Now the question is which one you are going to select. So you have to select in such a way that your weight is not exceeded this W, but your profit is maximized or the reward is maximized. So in order to model this problem, we have to first define the decision variables. So we define in this way. So xi, whether the ith element is selected, ith item is selected or not, and each element, these variables can take value between 0 and 1, because either I have selected or I have not selected. The constants that I have is, if I select xi, then it will contribute as wi, and if I sum over all the items, it must be less than capital W, which was given as our constraint. So that is the only constraint that I have, and now I have to define an objective function on the optimization function that I would like to optimize, and in this case we would like to maximize my profit on the reward. So if I choose a particular item xi, then it will give me a reward of pi. So I would like to maximize this one. So this is again the similar problem, but only thing we would like to optimize the total reward or the total profit, and this is famous. This problem is known as a knapsack problem. There are other problems as well, so I just I will quickly go over this problem. So you have to plan for warehouse. So what is the problem? So there are n possible location to set up your warehouses, and which will deliver goods to m customers. Okay, so you have n possible location to set up warehouses and n m customers. The cost to set up wj warehouse is fj, or fine, and customer ci has a demand of di, which needs to be fulfilled by the warehouses, so any warehouses, and the delivery cost per unit item from wj to ci is cji. Now target is to minimize the total cost to serve the required demands. So you would like to, what we need to do is we need to plan the warehouses, because we have to we know the demands of the customer, we know the possible location of the warehouses, and we have to now select the location of the warehouses such that we can minimize the total cost that we need to serve to the customer demands. So let us look into the set of constraints. First we will go with the variables. So we will have xj as the warehouse location, which will be either 0 or 1. That means I am choosing that location and I am not choosing that location, and the amount served by wj to ci is the demand that can be fulfilled by the warehouse wj, and this we do not know how much it can deliver, so we can say that yji can be from 0 to infinity. If we choose a certain place, and then it can deliver whatever amount it wants to deliver. Now the constraint is like, if I sum over yj, if I sum yji over the j, that means I have a customer c and there are many warehouses that are delivering here, and this summation should match to my di, because I have to fulfill the customer demand. Fine. Also, what we need to see is this one, like if I and the amount that will be generated from a location should be so the amount it is being delivered to a particular location will be more than its so the sorry, I should say in this way, so the generation capacity should be more compared to or the number of item it is being generated at a warehouse should be more compared to your demand, because then only you can actually fulfill the stuff. uh, uh, so let's say what does this actually mean. So so you have yji and you are summing over I. That means how many items you are actually producing or how many items are being served by jth location. Fine, uh, because this location is serving customer C1, C2 and so on. So I just want to find out how much it can actually serve. And if I look into the other way, that if I look into the demand, there is the di for each of these place, and then this sum of the demand over all I should be actually more if I choose xj to be uh, uh, no, so if I look into this one, so this will be definitely one, this will be definitely more. And if it is serving, or if I select the xj as 1, then still this will be actually more, because it can be it can at most be 0, or it will be less than 0, because there can be other one that can deliver. So this is the that constraint that we have to write. And the optimization function the optimization function is that how much cost I have to bear for uh, for choosing the warehouse, and how much cost I have to bear for delivering the actual item. So that we have to sum up. So that will once we give this set of constraint to the solver, I can find out the final solution. The crossword puzzle that I was talking earlier, this is just an example. So let's say I have been given this crossword, and I have to fill these places only with this set of words that have been given to me. Now in order to model this problem, is we need to define the variables. So what we can do, we can say that we have a variable r1, which basically means what I can put on this row. So when I'm having when I have this one, that means I have to put a word which is 5 which has 5 character. Similarly, there can be another word c3. So c3 is a word which has only 4 characters. Similarly, and so on. Similarly, for I can have a word here, I can have a word here, and so on and so forth. So we can define the variable in this way. Now the thing is, so when I said this one, then r1 can take the values only this set. So it can take only values which has 5 characters within it. Similarly, c3 can take all those values which has 4 characters. So c3 cannot take horses, c3 cannot take laser. Similarly, also cannot come in r1. Now now when we have defined these variables, we know the constraints, we know the domains. Now we have to write the constraints. So the constraints that we need to write is that if I look into the third character of R1 and if you look into the first character of C3, then they should be the same. Now wherever there is a overlap, I just need to write uh, a constraint for that one. So I can define in that way, then we can find out the final solution. So I have to write the constraint in this manner, so which should match. So this is an exercise problem, so I will just explain the problem and probably you can do it at your home. So what is the problem? So you have to pack the following words in this 8x8 board. Only you have to fill 0, 1, 2 up to 10 here. So that means, so there are few constraints. So all these words can be placed either across or downwards as we do in the crossword example. Fine. No letters are adjacent unless they belong to one of the given words. So that means it can happen in this way, like I can put Z, E, R, O and I can have 1 here. So no letters are adjacent unless they belong to one of the given words. The words are rookwise connected. That means either it will be connected in this way or it can be connected in some horizontal or in, so it can be connected in this manner. So it cannot be something like I can say in this way, like so I cannot put in this manner, I cannot put FOUR. So that means it has a wide connection, that cannot be possible, but this connection is possible, like so rookwise connected. And words overlap only when one is vertical, the other one is the horizontal. So that means I cannot have this situation ZERO, this is not possible. So with this set of constraints I have to fill this table, or I have to pack this set of words on this board. So this is this you can treat as an exercise problem and you can solve it. Thank you very much. So in this lecture what we have seen is how to model a problem in CSP and how to write the set of constraints. So we have to define the decision variable, we have to define the domain, we have to write the constraint, and if there exists any kind of optimization function, that then we have to write the optimization function. In the next lecture we will see how to solve the set of constraints. So thank you very much.